Hello everyone, this is our submission for the M5 final hackathon M4 classification challenge. Our objective was to develop a responsible AI model for stroke prediction, ensuring fairness, transparency, and interpretability while maintaining high predictive performance. Stroke is a leading cause of disability and death, and early detection is very critical. However, AI models in healthcare can introduce bias, potentially leading to unfair treatment recommendations. My approach integrates fairness constraints, explainability techniques, and ethical analysis to ensure the model is both accurate and accountable. For the first part, data preprocessing and handling imbalance. Before training the model, I conducted extensive data preprocessing to improve model reliability and fairness. Key steps included first, encoding categorical variables to make them compatible with LetGBM. Second, authorize removal using the 2-key method, ensuring extreme values do not distort predictions. Third, feature scaling with standard scalar, min-max scalar, and robust scalar for numerical stability. One of the biggest challenges was class imbalance. Stroke cases were heavily underrepresented. To address this, I applied SMOTE, which generates synthetic samples for the minority class, ensuring the model learns patterns from both stroke and non-stroke cases. For the second part, model training and ARIA implementation. With the data prepared, I trained a LetGBM classifier, which is efficient for tabular data. However, raw models can exhibit biases, so apply Fairlearn's exponentiated gradients technique to enforce demographic parity constraints. To validate performance, I used stratified K-fold cross-validation, ensuring stable metrics across multiple data splits. The model achieved accuracy of 95.24% plus or minus 0.35%. And other metrics achieve these results. In a healthcare setting, recall is particularly important. Underestimating stroke cases can be life-threatening. Where my model balances precision and recall while optimizing for fairness introduced a trade-off, which I carefully monitored. To measure fairness, I computed demographic parity differences, which is DP equals to 0.0162 plus or minus 0.0069, and equalized O's difference, which is EO, equals to 0.0173 plus or minus 0.008. This low value suggests that the model does not heavily favor one demographic group or another, although minor disparities remain. For the third part, model interpretability. Ensuring that AI decisions are transparent and understandable is crucial, especially in healthcare. I applied multiple explainability techniques to achieve this. First, for the global feature importance. I first analyzed permutation feature importance, which showed that age dominates stroke prediction, which counts for 40% 7% aligning with medical knowledge. BMI and average glucose level contribute, but hypertension and heart disease had surprisingly low impact. And second, for the SHAP. To further verify these findings, I used SHAP, which confirmed that age is the strongest predictor, but also revealed that higher glucose and BMI levels increase stroke risk. One key fairness observation, gender had minimal impact, suggesting that the model is not making biased predictions based on sex. And third, for the local explanation, How are individual predictions made? For case-specific interpretability, I applied LIME, which allowed me to break down single predictions into understandable contributions. This helped verify that this model was making logical, medically relevant decisions. Finally, the decision tree circuit model, which will make LegGBM more transparent. To further simplify LegGBM's decision-making process, I trained a decision tree circuit model which mimics the complex model in a more interpretable form. This tree revealed that age is the primary decision factor, with different age thresholds determining stroke risk, and work type and BMI influence later decision stages. Gender and residence type play little role, reinforcing fairness. By using multiple explainability techniques together, I ensure that the model's logic aligns with medical reasoning and fairness goals. For the fairness and ethical considerations part, while my model performs well, fairness and ethical implications are critical in healthcare AI. My analysis found that urban populations have higher stroke rates, likely due to lifestyle and healthcare access factors. One potential concern is that age dominates the model's performance. While this is medically expected, it is important to ensure that age-related biases do not result in unfair prioritization of healthcare resources. To further improve fairness, potential enhancements include adversarial debiasing, a technique where a secondary model helps remove biased decision patterns, reweighting techniques, adjusting the importance of underrepresented subgroups in training. Ultimately, while fairness constraints help to reduce bias, ongoing monitoring is needed when deploying AI in real-world medical settings. And for the conclusion and bias impact parts, in summary, this project successfully integrated the responsible AI principles into a stroke prediction model by ensuring fairness, interpretability, and strong predictive performance. From a business and deployment perspective, this model could assist hospitals in early stroke detection, allowing doctors to prioritize at-risk patients. However, continuous fairness monitoring would be essential to prevent biases from creeping in over time. Feature improvements include integrating causal inference techniques, more diverse datasets, and real-world clinical testing to validate fairness. Thank you for watching.